So are we filming yet, Tom?
Do you want me
Okay. For them,
I'm a rising junior at Lhasa High School here in Austin.
Okay. So today we're going to be talking to you all about taking a selfie. And hopefully by the end of our presentation, you'll know all about the static equipment for the lunar filming and imaging of Earth.
So here is our mission patch and a 3D model of what our lander might look like.
So this picture is called Earthrise and was taken on the Apollo 8 mission, which was the first time humanity had ever ventured out beyond low Earth orbit. And this picture was kind of the first time we ever saw ourselves at a distance. And there's the astronauts on the Apollo mission, when they came back, even said, we came all this way to explore the moon, and the most important thing we discovered was the Earth. And with this image, for the first time, we realized that Earth wasn't the color-coded, segmented ball that we all grew up with in school, but is actually a fragile, unified island floating in the sea of space, and that it needs to be maintained and protected. So sadly, in the 48 years since that picture was taken, the humbling and inspiring effects that that picture had on us seem to be starting to fade. So we really need to find a way to get more people to realize that spaceship Earth is our fragile home and it has to be maintained and protected. So that's what the Selfie mission's goal is. It's to provide everyone on Earth who has access to a phone, tablet, laptop, TV, anything with internet access to near real-time video and images of the Earth as seen from the moon.
So the overall goal of the Selfie mission is psychological, not scientific. So how many of you here have seen Sagan's pale blue dot? Show of hands. So Sebastian threw out a few quotes earlier. You probably recognize the words, or at least how you felt when they were spoken. So I'm going to attempt to use Sagan's practitioning and combine English and science for a second here to give you an idea about what Selfie is all about. So some of you might be skeptical of words, of the way they twist meaning and bend will, especially in politics. And but the thing about words is that they're what leave the greatest impact. They're what inspire us and what innovate. And some say that words are what make us human. They're what tether us to one another and tether us to our identities. They are a golden ticket to worlds we never dreamed could exist, parallel to our own. And our key to unlocking generations of knowledge that have been gifted to us with little else than a simple request to use it wisely. But as those of us congregated here probably know, scientists aren't the best when it comes to using their words. So bearing this in mind, I ask you this. Why bother cloning Neil deGrasse Tyson 100 times over for his artfully crafted words when a picture is worth 1,000? This is our team's motivation behind the Selfie mission. Listening to Pale Blue Dot, seeing Earth rise over the moon, or watching one of our own set foot on a celestial body suspended hundreds of thousands of kilometers above our heads, something that was in the past just a thing of myths and legends. These are the moments that left their imprint on each and every one of us. But in recent years, space seems to have lost its mystery and glamour, that lost the hook that could ensnare even the most skeptical of minds, even the most apathetic observer. And that hook is actually why all of us are here. Something got us interested in space, something got us interested in what NASA does and brought us to the SEAS program. Something launched the Saturn V, something that landed the Pathfinder of Mars. Because with our money drained our understanding that the world is so much bigger than us, it's so much bigger than our countries and our wars and seemingly intolerable differences. So by viewing a live stream of what Sagan called the body where every human who ever lived out their lives existed, by watching its journey surrounded by the vastness of space, these fancy words and these humbling pictures are what we need to restore humanity's love for discovery, and this is our Selfie mission.
So let's talk about our landing site. We have two pre-planned landing sites, Mare Imbrium and Mare Serenitatis. So we chose these two landing sites because one, they are flat, so it's easy to land on, and two, they were the sites of previous Apollo missions, so that we know they will be reasonable places.
So here are some things about the lunar environment. First of all, there's practically no atmosphere. It's very tiny, But even one Apollo mission, the exhaust from the lander could double or even triple the amount of gas that's in the atmosphere. And since the lunar month is about 28 days and it's tidally locked to Earth, that means that the 14 days that it's light outside are really hot. It's around 171 degrees Fahrenheit because of the little atmosphere. And then the next 14 days are very dark and very cold, about negative 225 degrees Fahrenheit. Also, it is exposed to solar radiation and cosmic rays, so that's something that we'd have to incorporate into our design by radiation hardening the electronics and that type of thing. So here's an image of the lunar topography. So the blue areas are the flat ones, and then the red is mountainous or steep regions. So here are our proposed landing sites, the Mare Imbrium and the Mare Serenitatis, and as you can see, they're very flat, so they would be ideal landing sites. Our mission requires several different subsystems: the camera, power, thermal, communications, and the rocket system. So, first of all, the camera. So this is really the backbone of our mission. It's the whole reason that we're going there is to take pictures. So we wanted really high quality pictures that would really inspire the viewer. So to do this, we took 4 cameras that are already high quality. They're 3,326 by 2504 pixels. But we put 4 of them in a grid so that they would all point at different quadrants of the Earth. And then we stitch them together to create a very high quality image. And this is so that the user can select a location and zoom in while maintaining the high quality of the image. So these are the camera and the lens that we chose. So here's a CCD camera and an 800mm Nikon lens with a 5.6 focal ratio. These are consumer cameras, so they may not be able to be used in space, but we can either radiation harden them and space proof them, or just make mechanisms that are similar in the technical aspects. Also, from when you view the Earth from the moon, it moves around in the sky, so we will need a tracking mechanism to track the Earth so it doesn't move out of frame. And whenever the sun passes in a frame, then it could damage the cameras, so we're going to have a mechanical lens cap mechanism that covers it to protect the camera.
We also decided that it would be a good idea to have a video camera on board our mission. This video camera has its own needs. We decided it had to be able to send a 1920 by 1080 resolution, continuous and reliable video stream back to the Earth. For these reasons, we decided we chose to model our camera on the Canon EOS 5D Mark III. It's also a consumer camera, but it has a wide range of manual controls, a large sensor, and is incredibly reliable in the field. We chose to pair this camera with a 250mm lens. So that's a number, but what does it mean? We calculated that the Earth would occupy like 2 degrees of the total field of view of our camera. But when we pair it with this lens, the lens in the camera will zoom into like 6 degrees. So the Earth will be a little like ball in the center of the camera's field of view. Much like the still cameras, the video camera will have a mechanized lens cap to shield it when the sun is in view, and it will be able to inherit the tracking system from the still camera array. It supports many popular compression formats, so that means that it will be easier to transmit the images at a lower bandwidth cost than it would be if you were to just transmit like the raw video. We estimated this camera to have a TRL, which means technology readiness level, which is literally like how ready the technology is to go into space, of 5. This means that it hasn't gone into space yet, but it is a widely tested and very popular consumer camera.
And the scale is out of 9, just so 5 out of 9.
Oh. So now that we have all these pretty images, we need to figure out a way to send them back to Earth, or they're kind of useless. So we looked into both radio frequency communications and laser communications. Ultimately, we decided that a laser communication system would be much better than the radio frequency communications because it is low power, low mass, and high bandwidth. Our design, which is based on the design of the LLCD, which stands for Lunar Laser Communications Demonstration, that went off on the LADEE mission, which is Lunar Atmosphere, Dust, and Environment Experiment, will get 622 megabits per second from the moon to the Earth. Coincidentally, that's like 300 times faster than my home internet. It's composed of two main parts, the space terminal, which is LLST, and the ground terminal, which is LLGT. We'll be able to reuse the ground terminals that are already on Earth that were set up for this other mission. The only thing that we're going to have to bring up with us is the space terminal, and it's pretty light. Because it's so light, we decided to bring up two communication systems for redundancy. Just in case one fails, we'll have a backup that uses little mass, and obviously it'll be turned off so it doesn't use any power. This has a TRL of 9 because it's already been tested in space. All right, and so now we have to find a way to power all of our systems that we're taking up there. So we have our laser transmission system, which would take about 76 watts. All 5 cameras would take 168 watts, and for a grand total of 244 watts of power, which will be generated by solar cells. So for our solar panels, we found that the most efficient solar cells to use were the next triple junction XTJ solar cells made from gallium arsenide and silicon hybrid material, which is very hard to say 5 times fast. So let me break this down a bit so that it's easier to swallow. So triple junction means that there are multiple materials used in the solar cells, which means that there are multiple band gaps. And so then you can absorb more light wavelengths into your solar panel and get more use out of your sunlight, because if you had a square meter of sun, then you'd get 1.3 kilowatts of power, but solar panels are only 30 to 40% efficient with our current technology. So the best we could do was 345 watts per meter squared, but that still give us 862.5 watts per panel. And these are extremely efficient because normally your band gap, which is the minimum amount of energy required to excite an electron from its base state into a freed state where it can conduct electricity. Usually a photon with too much energy knocks into your solar panel, releases the electron that has too much energy, releases that by banging into the matter around it, which ultimately converts into thermal energy, and thermal energy degrades your solar panels much faster. So instead of losing all of that energy and then converting it into something that would destroy our panel, we're utilizing more of this. And this technology was actually used in NASA's Juno mission. So it's 50% more efficient, it has radiation-tolerant wiring, and this area-conserving folding design that's perfect for our mission. And so these cells are also not in series, so if we have defects, then the panels should work just the same. And we also added 2 solar panels with a 2.5 meter squared area for our entire design for redundancy. And then we only need 244 watts of power, and we have 862.5 per panel. So all of this extra energy, we'll explain where that's going later on. And it has a TRL of 8.
So solar panels are good, but they don't work at night, so we need to work around that. We were looking at alternative forms of energy generation like RTGs, which are radioisotope thermoelectric generators, but we ultimately decided that those forms of generation are too expensive and too dangerous for what we needed. So we settled on using regenerative closed-loop fuel cells. So what is that? So these type of fuel cells are fairly similar to normal fuel cells, which are diagrammed over here, but they can also reverse the process. So let me explain. During the night, the fuel cell would combine hydrogen and oxygen to create water and electricity, so that we can power everything during the night. During the day, with the help of the solar panels, what we can do is reverse the process so that we can break up the water into its hydrogen and oxygen components. So we can store these in tanks and then use them the next night. This is a picture of what one of those fuel cells would look like. These fuel cells have a TRL rating of 9, and the modern specs of these are 600 watt-hours per kilogram. down here we have the dimensional analysis for how heavy it is. So if you like math, that's okay.
And then also with these closed-loop fuel cells, they're significantly more durable than batteries, so they can outlast our solar panels, which have a predicted functionality of 10 years. But they are less efficient, so they don't store as much of the energy as you put in them. But all of that extra energy we have almost more than 3 times as much energy as we need. We will store that into the closed-loop fuel cells for the 14-day lunar night, and we will also use that to power our thermal system to keep everything safe from the lunar environment.
So speaking about the thermal system, as they stated earlier, the temperatures on the moon can range from very low in the negatives to very, very hot, over 200 degrees. And so we decided we need a very efficient and reliable thermal system. So we decided to go with the phase change material heat exchanger, as well as the classic multi-layer insulation, as well as the use of radiators to help disperse excess heat during the days. So here are 2 pictures of the MLI multi-layer insulation, which is used almost on every space mission, giving it a TRL of 9. And now the phase change material heat exchanger is imaged here. This system pictured right here is actually on board the International Space Station right now being tested. So we decided to give it a TRL of about 7 to 8. And the phase change material that it uses is based off of N-pentadecane wax, which you can see around here, like around the outside of the system, the yellow, in conjunction with the coolant liquid that will be pumped through the rest of the system. Then through here, during the days, the heat will be transferred into the wax, melting it, thus storing the thermal energy. And then, of course, the coolant will then be colder than it was when it entered and go back through the system to do the same again. And then during the nights, the process is essentially reversed. The same coolant is pumped through, and now that the entirety of the system is cold due to the lunar night, it'll pick up thermal energy from the phase change material around it, which is now melted and very hot, and thus heating up the coolant and be pumped through the rest of the system to keep it warm. And like I said, a TRL of about 7 to 8. Now, our total mass calculations for the entirety of the system, not including the rocket and that, we included everything that would be on board the system, including our redundancies. So our 2 transmitters, the 8 still camera lenses, the 8 still cameras, the 2 video cameras, the 2 video camera lenses, the fuel cells, the solar panels, and the thermal system, to a total of about 560.84 kilograms. And then we included a mass margin of about 12% because, as we learned from Mars Bound, like they talked about earlier, things in space missions always change. So we included a margin of about 12%, bringing us to about 628.14 kilograms, which is well below the max capacity of the rocket we'll be using, which we'll talk about more later.
So the trajectory that we're going to use to get to the moon involves 5 burns. So the first one is to escape the Earth's atmosphere and enter into low Earth orbit. The second one fires us out of low Earth orbit, thus beginning the homing transfer orbit, which is the figure 8 path to the moon. Then we'll fire it again to slow us down enough to enter lunar orbit. A 4th burn to begin the descent towards the surface of Mars, and then the final burn of the retro rockets to slow us down enough to land safely on the surface.
So we went shopping on the NASA website in the query to search for a good rocket to use, and eventually we settled on the Atlas 551 short rocket. So the C3, this is a measure of energy in kilometers squared per second square that we need to get to the moon is around -1.95. So then our mass after the translunar injection, or the TLI, will be 2,210 kilograms. And the cost of the entire launch process is about $164 million. This is a picture of the rocket, and this is the graph we used to figure out the mass of the translunar injection, after the translunar injection. So these equations over here have been kindly provided by our mentor, Professor Fowler, and we have used these equations to calculate the payload mass. Essentially, this utilizes the rocket equation over here-ish, which is which uses the change of velocity, the C value, which is the exhaust velocity, the M0, which is the initial mass, and MF is the mass after the burn. So after doing the math, we figured out that the max payload is about 666 kilograms, which we said before is way over our mission payload of 630 kilograms. So we have a lot of buffer room.
So our lander is called Stick, so it can be Selfie Stick. So we have retro rockets on the spacecraft to slow down when it enters orbit and help it land on the lunar surface. Like we said before, we have 4 still cameras and 1 video stream, and we have an extra set for each of these cameras for redundancy. Our main sources during the day is a dual solar panel, and the night will be a generic closed loop fuel cells and a thermal system. We also have a transmission system on board. Okay, so here we have a rough draft basically of how it will look. We have the cameras here, you can see them, but you know the cameras right here. And then we still would have to put like the thermal system and the retro rocket panels. We have the solar panels right here, and that's pretty much it. STIC stands for the Systems and Technologies of Information Cameras of Communications. Then we have our cost calculations. So the mass inside would be 628 kilograms. A fabrication complexity would be an average, and our much would be in 2020. Our boosters are about $164 million $2020, and then our total mission cost would be from $311 to $520 million, depending on who is working and who's making it. Our calculations are courtesy of Dr. Mandel, retired NASA engineer.
Okay, so a lot of our weaknesses in this particular mission were resulted from the lack of time. We simply didn't have time to get past anything beyond like preliminary estimations for payload, mass, cost, and a couple of other things. Although our cameras are untested in space, given more time, we could look deeper into what exactly it would have to do in order to make them space ready. We don't have a super detailed design of the descent vehicle yet, but again, there's so much more prior information that we just have to look it up and learn a little bit about it more. We also don't have a geometric layout for our payload, which could cause imbalances in the rocket system when we launch it. However, given the time that we had, our mission is remarkably robust and redundant. We have a lot of additional power. Our camera systems will work. Our communications have more than enough bandwidth in order to be able to handle the signals that we're sending through it. Our booster choice is capable, and we know a lot about the landing site, given that many missions have landed there before.
So, takeaway-wise, well, now we're just going to take a moment to kind of talk about the program as a whole and our experience here. Now, I came into this already knowing that I wanted to do something in the space industry in my future. I've always loved space ever since I was little, and for years now I've known that I want to do something in the space industry when I'm older. So being able to come here and learn so much from people that work in the field and have been working in the field for such a long time and know so much about it was just an experience that couldn't be replicated anywhere else. It was fantastic. Like all of the little things that we got to do on top of the amazing work that we did, like going to Johnson and all of the other things that we got to do, Mars bound as well, outside of our main projects to help us learn other little things that we may not have picked up solely from our projects, just made the process so well-rounded and fantastic that it's, again, one of the best experiences, probably the best experience I've ever had in my life. And the only suggestion I could say is, like we said in our project, maybe a bit more time, because some of the projects that we're doing and the research we're doing involves a lot of time to work through. So just having more time would be fantastic and make the program even better than it already is.
For me, I have to echo Sebastian's sentiments about how this has been an incredible experience. Really what I learned, or what I took away from this program was at Johnson Space Center, when we were being given the tour of the Saturn V rocket and how it went through space, how each little bit of the mission made it work, it was just fascinating, and it made me really think about how you don't just have a rocket, light it, and it goes to the moon. A lot of people don't understand that even in computers and their iPhones, lights, anything, any system, engineering is so difficult. It takes months and months of time just to make a rough outline of what you want to do for the project. And so with engineering, with even different sciences, it's just the amount of work and time that goes into it, and the amount of different sciences you can go into. It was just wonderful that we got to see that, especially at at Johnson Space Center, because we went to, once again, geology labs. We saw divers that worked in the space program, pretty much. And so just knowing that that all of those fields, I could work with space, engineering, anything. It was completely worthwhile, and it just made this whole experience fantastic. So thank you.
So my biggest takeaway is I enjoyed working together with my group, the 6 of us just working together. It felt really satisfying to go through like information, compile it, making this presentation, like making our mission. And I just wish I had more time to work with these guys, because they're like all of us, like we are like-minded people who like science, and like we're not like slackers, we actually work. So it's just a fun experience, and a lot of this was uncharted waters for me, and I'm pretty sure for all my group it was just uncharted waters. We had no idea what we were doing, but thanks to our great mentor, Dr. Fowler, it was a lot of fun. Sometimes it was frustrating, but yeah, it was great work.
Yeah, I think my biggest takeaway was be able to see so many different people, so many different interests in space, not just in space, but a lot of people here also not just focus on space, but like wanted to have a general overview of what is possible and what we can choose in the future. And so it opened my eyes that space does not just have to be aerospace engineering or something to do with space, but we can also be in a career field and also be healthy.
I think for me, the most valuable part of the program was seeing how engineers like break down problems. I think at the beginning of the summer, we all got an email like for our task 2 stuff, and the first line of the email was like, our goal is to design a system that will put a camera on the moon. And I had no idea what I was supposed to do. But thanks to Dr. Fowler and everyone else who helped us out, it became really approachable, even though it's definitely complicated, and I basically didn't know how a camera worked before this. It was really interesting to get to learn how to break problems down into something that seems easy-ish, kind of.
Yeah, I think this program was very, very worthwhile in the way that I have never done this much research on an engineering project in my life. Normally, like, the research stuff that we have to do at school is history or English or things that aren't necessarily my favorite subjects. So this was really fun to research, and it gave me a new appreciation for that kind of stuff. Also, the one thing I would improve is also more time, because in addition to this main project, we had lots of little activities scheduled, like egg drops or hot chocolate machine or something, but some of those ended up getting canceled because we all were feeling stressed about these presentations, and we had to kind of rush through everything. So yeah, I would like if there were a little more time.
And then, of course, a special thanks to Dr. Fowler and Ms. Baggio, everyone who works at CSR and the C staff, obviously to NASA, and just everyone who made this experience possible, even our fellow interns. It was just an amazing experience, and I couldn't thank you enough. I'm sure all of us feel the same way. And any questions?
Why do you rank your TRL out of 9 instead of 10?
That's just the scale that's used in the industry. It's each level has a certain definition. So if it's like, say, 0 would be just like an idea, like just if it was theoretical. So the theory of relativity, when it was first written, that would be it's 0 because it's theoretical, hasn't been tested. And then a TRL of 9 is like it's been in space multiple times. It's been used, like the multi-layer installation. It's on everything. Everyone knows it works in space. It's not a problem. So yeah.
So, first question, is the moon rotating?
Yes.
The moon orbits Earth. It's tidally locked, so it orbits facing the same side, but it still has day-night cycles. Because say this was the Earth and the sun was over here. When the moon's over here, the side facing us is lit up. But when it's over here, the side facing us is dark and the opposite side is lit. So it still has day-night cycles, but it doesn't rotate about its axis.
That's why we never see the dark side of the moon, is what they call it. But when we have a new moon, then that's when we would be in our night cycle.
Anyone else? Yeah.
So how much did cost constrain your preliminary design?
When we started off, we were just kind of, first we wanted to figure out how we could do this and what would work to make this happen. So we didn't consider it all that much at first, and then towards the end we factored it in, and then from there, with the amount of time we had left, we started kind of cutting things off and changing things and using other systems instead to try to reduce the price from that point.
There's also something extra that we could have added, but in the manufacturing process, you could use additive manufacturing, which is something that they used on the Juno mission, and it saved them a lot of money. So if we were going to continue with this and move down the line, then we'd see what processes there were for us to cut costs. That was Emma.
So you mentioned you did all the calculations for how to get all of your equipment to the moon, but what about assembling it on the moon? You would have to send like astronauts there.
The system would be pre-assembled. If the only sort of assembly that would be required is if we found a way to fold it up to maybe fit it in the payload bay of the rocket and to make the center of mass more steady for the rocket, and then it would just self-deploy once it landed. So it wouldn't require astronauts at all. No. And then you had your hand up.
Oh yeah. So is the content you're producing, would it be available to consumers or?
Yeah.
We looked into distribution, or had we had more time, we would have looked into distribution through television networks, but also through internet. There's obviously lots of streaming sites out now that would make it trivial to just send a signal that we're getting off to one of those with minimal processing afterwards.
So and another big idea behind it would be making it into a phone app, so that anyone could pull out their phone at any time and be like, oh, that's what the Earth looks like right now from the moon. So that was kind of good. Yeah.
Well, just to add to something, all NASA images are public domain.
Yeah.
So you need access to it just because it's a funding side.
Yeah. That's what he said.
That's in the Martian field when they have to tell people that they're over the moon.
Yes.
Any other questions? No?
Good
All right.
job.
Thank you.